Okay, we are continuing our discussion on acids, bases, and salts. We are still focused on acids. So by now, you know the definition, you know what is called hydroxonium ion, and you're able to know different types of acids depending on the class that they decide to use. Can be based on source and others. So for now, we are going to physical properties of the acid. Normally, when you say physical properties, you are referring to properties that do not involve chemical change. I think that's one of the first things you do in chemistry. You have physical and chemical change, and as a result, you also have physical properties and chemical properties. So physical properties they don't involve chemical change; they just happen. So basically, you can say there is no chemical reaction. So most of the times, these things they involve the five senses. Oh, what is the taste of the acid? How does the acid smell? You can see the senses. What does the acid look like? Talking about what you see with your eyes. How does it feel to the skin? Those are the properties that you're looking at. It goes beyond that. There's also, in terms of physical properties, what is the weight? But in this case, we won't be looking at really what weight is all about. So first of all, the physical properties, the one that is always very popular, you say acids turn blue, litmus, red. Later we'll discuss indicators. Litmus is a type of indicator. So technically you can also add other indicators. Like you can turn phenolphthalein colorless. But because litmus I think is the most accessible, litmus is preferred and you can easily get litmus paper and use as compared to others. Use and reuse for litmus paper. So it is used as part of the physical properties. So the physical properties of the acids can be very many, but it is restricted to a particular number. It all depends on who is speaking. So acids on blue litmus, red. Another one is that acids have sour taste. And we spoke about types of acid at that time, and you could see that in almost everything that you have, natural things, they all contain acid. Talking about organic acids in this case. And if you see most unripe fruit, they are sour. Why? Because at that point, their acid levels are very high. Same thing happens for food. When it goes sour, that means the acid content has also increased. So acids have sour taste. Then the next thing we speak about is concentrated acids are corrosive. Corrosive means they are very reactive. Reactive to the extent that they can cause burns. That is the next part you have to talk about. So very reactive and corrosive, there's like a thin line between them. Corrosive means it can get to the extent of causing burns. And so you see that when people come in contact with concentrated acids, they get burns. And as a result, these acids they are stored in special containers. You don't just put them in you don't put them in any form of containers. They are put in special containers, which you can use to store them for a long time. For some other specific kind of containers, you can put them there, but only for a short and a very brief time. And so that now takes us into the idea of concentrated and dilute. And this is a concept that you're going to be seeing a lot. That we have concentrated, talking about, you can use it for acid, but it's the same idea when you move on even to other compounds. So, concentrated and dilute. When it comes to concentrated and dilute, the concept we are discussing here is the amount of water involved. So, again, let's go back to a little concept you should be able to remember, that we have what we call solids and we have what we call solvents and we have what we call a solution. Solid is the thing that is being dissolved in something else. So if you take salt and you dissolve it in water, salt is the solid. The one that the other guy dissolves in is called the solvent. Then when the two of them are combined together, that is called the solution. And so when it is concentrated, what that just means, again, you can see now that you can say an acid in this case is a solid. And they are dissolving it in water, that is the solvent. Then together, it is a solution. We spoke about in the previous video, where you have HF, can be hydrogen fluoride. But when it is now dissolved in water, then it becomes hydrofluoric acid. It is now in solution form, dissolved in water. So now when you say it is concentrated, what that just means is that the acid content is greater than the water content. That means there is more acid than water. That's the meaning of concentrated. And so you can be hearing these things as you move further. To concentrate an acid, it means you have to remove water or you add more acid to it. Why? Because the amount of acid needs to be greater than the amount of water. That is concentrated. But what is dilute? Dilute is now the reverse. The acid content is less than the water content. So that means that the amount of water is more than the amount of acid. That is what you refer to as dilute. And remember, whenever an acid is in dissolved form, again, it goes beyond acid. We can extend it to beyond acid later. That is called an aqueous solution. And so you will be saying things like HCl in brackets, AQ. That means, oh, there is some amount of water involved in this particular substance that has been dissolved. So that is concentrated and that is dilute. So concentrated acids are corrosive, and that's why in the laboratory, for students to work, they mostly use dilute acids, especially in chemical reactions, because it is safer. So you can have a concentrated acid, if you mistakenly touch it, you are in trouble. But if it's diluted acid, if you touch it, you are not in so much trouble because you don't get burnt. It is now dilute. Now remember, we have spoken about it. To concentrate an acid, it is either you add more acid to the solution or you take away water from the solution by evaporation. You take away the water. How about when you want to dilute an acid? To dilute an acid, that means that you need more water. So what do? You simply add water. But this is not a little trick. When diluting an acid, you don't add water to acid. You add acid to water. If you should add water to acid, it can, what's the word now? But it can splash. The acid can splash and it pours on the person who is doing the dilution, and that becomes a problem. So the safe bet is add acid, add it to water. The idea is that when you add acid to water, the water acts as a heat sink because it's very corrosive. When you now add it to water, the water is able to act as a sink that is able to regulate the amount of heat. Because when you add water to it, that heat is what causes it to splash up, very corrosive and very hot. If you go to a place where a can of concentrated acid is open, you see the amount of smoke that comes out of it. It is quite hot. So that is the concept between concentrated and diluted. So concentrated acids are corrosive, not dilute acids. And take note, no matter the acid, whether strong or weak, as long as it is concentrated, it is corrosive. So take note of that. Concentrated acid concentration does not determine whether it is strong or weak. And strong does not determine the concentration. Concentration is just talking about this particular acid. What is the content? What is the amount relative to water? If the amount is greater than water, it is concentrated. If the amount is less than the amount of water, then it is dilute. As you move further, you get to learn of things that like azeotropic mixtures. When you are trying to concentrate and you are trying to dilute, or some say constant boiling mixtures. I think that will be an assignment. Try to find out what it actually is. What is an azeotropic? What's an azeotropic mixture? So find that out. So those are your physical properties of an acid. Like I said, people can escalate it beyond just these three. An example, people can begin to talk about the pH, which we are going to be discussing in further videos. So in the pH, some can say, oh, the pH is less than 7. Can escalate it beyond that, but these are the three major ones. So it all depends on who is speaking with you. So if I am speaking with you, work with the person and know the amount to use. So the number of properties that you can use. Those are physical properties. Remember, those ones don't involve chemical change, they just happen. And you can see they mostly involve the senses. Next is chemical properties of acids. So what this one means now is it involves chemical change. Again, people can go beyond the three I'll be giving here, but these are the major three, which you are going to be finding out or using even as you move further in chemistry. So you are meant to learn these properties so that as you move to the next level in chemistry, such concepts you are able to easily apply them. And that's the beauty of chemistry. You don't need to cram it. You're able to understand the concepts. So when you are moving forward later, you are able to grasp many of these concepts. Now, the first one is that acids react with metals to liberate, oh, sorry for my liberation, to liberate hydrogen gas. Most times, I don't just like giving the stories like this. I like giving chemical equations which are involved. So what do? We are going to take an acid, we are going to take a metal, and then we are going to show the chemical reaction. Now we know when acids react with metals, they liberate hydrogen gas. They actually give two products. But then again, as you are moving further in chemistry, you get to find out that at times, to signify the end of a chemical reaction, you try to check what is produced. What is the evidence of a chemical reaction? And in a chemical reaction like this, what is the evidence? You start to see gases being produced. And how do you see gases being produced? You start getting bubbles. Bubbles shows you that, oh, this reaction is happening. Those are evidence. At times, you get a precipitate. And in some certain reactions, where you don't get proof that the reaction has happened, you have to use something that will show you that the reaction has happened. And that's why when you get to titration, volumetric analysis, reaction between acid and bases, you use an indicator. With use of indicator, by the color change, you are able to know, oh, the reaction has happened. So when acids react with metals, there are two products. But the beauty is that one of the products is able to show you that the reaction has happened. And what is that product? That product is hydrogen gas. I guess that is why it is used as the headline. So let's take an acid. Okay, we know HCl. Reacting with a metal, you can pick any metal. You have very many metals. So let's say we are picking sodium. When acids react with metals, it gives you hydrogen gas. It liberates hydrogen gas. That's why it says liberate, because the gas tends to leave the container. That's liberation. But what happens now? Take note of this. Whenever an acid is reacting with something that has a metal, the metal displaces hydrogen gas. That's exactly what happens. So what happens basically is that sodium, which is the metal in this case, it goes to the acid. When it gets to the acid, it pushes out hydrogen and replaces hydrogen. That means you come to where you have the acid, take out H and place Na and then Cl. And then you are liberating hydrogen gas. This is the reaction. But now if you check it out, the reaction is not balanced. So you can then balance the equation and place a 2 here and place a 2 here. And that is your answer. Again, in forming these reactions, this is where you have to practice it. In forming these reactions, you have to remember basicity. What is basicity? The number of replaceable hydrogen ions. So for HCl, the replaceable hydrogen is the H. Well, in this case, it's very obvious. It has only one H. That's what gets replaced. But now let us have an example, like ethanoic acid. Let's again use the same sodium. Again, what happens? The metal displaces hydrogen. But now when you look at this compound here, CH3COOH, from basicity, as we discussed in the previous video, all the hydrogens are not involved. There is only one hydrogen that is involved, which is the hydrogen that is inside the COOH. So that means that when you want to replace, you don't replace any other hydrogen, you only replace the one that is replaceable, which is the hydrogen in COOH. So you take the metal, it replaces that hydrogen. So you have CH3, COO, the metal replaces that hydrogen, plus H2. Again, why are we having H2? Remember, hydrogen, whenever it is standing alone, it is always diatomic. So it has to be a 2. So what will happen is, I will leave this one for you to actually balance it. Although it is not difficult, you can easily do it. It is exactly the same idea that applies to the first one that we balanced. All right. So now we can move on. Let's use one more. We have H2SO4 plus, well, let's say calcium this time. Calcium is a metal. Again, the same thing happens. If you look at H2SO4, what happens? It's an inorganic acid, so all the hydrogens are replaceable. That means they are all ionizable. So the calcium can replace that. So what will be your salt? Calcium comes here, pushes out hydrogen, so you get CaSO4 plus H2. And that becomes your equation. Again, you have to be careful about this. Watch my previous videos where we talk about getting formula of compounds. If you write Ca2SO4, then your equation is going to be wrong because that is not the proper formula for calcium sulfate. But you can check it out now. What are your two products? You get a salt and you get hydrogen gas. When an acid reacts with a metal. And that's the player you need. So by now, I believe you are balancing this equation. You should have a 2 here, have a 2 here, and have a 2 here. And that balances your chemical equation. So that's the first property. Acids react with metals to liberate hydrogen gas. The next one. Acids react with trioxocarbonates. Trioxocarbonate, again, the way I like to do it is, just know, trioxocarbonate is a radical, which is CO3. Again, to liberate carbon dioxide. Again, carbon dioxide is a gas. So the point here is that you have more than one product. But why is CO2 being mentioned? Because it's a gas, and that gas represents or shows that a chemical equation has happened. And how will you know? There will be bubbles. Some call it effervescence. EFFERVESCENCE. So they will say effervescence is observed. That shows that a reaction has happened by what you get. So now, trioxocarbonate. Let us get one. Trioxocarbonate, let's say CaCO3, that's calcium trioxocarbonate, reacting with an acid. We have used HCl, we have used H2SO4. So let's attempt to use nitric acid. So again, what happens? Always remember, whenever an acid reacts with a compound that has a metal, that metal will displace hydrogen ion. So, what is the metal here? Calcium. Calcium will displace hydrogen, pushes it out. So, what do we have? We have CaNO3. But again, remember, follow the previous videos on how to get formula of compounds. It's not just be CaNO3, it will be CaNO3 in a bracket, then you place 2. Remember, you have to exchange their oxidation numbers. This is a salt. Water is also produced, and then you get carbon dioxide. So you can see, when acid has trioxocarbonate, you get 3 products: a salt, water, and carbon dioxide. But remember, why is carbon dioxide used? Because it helps to identify, because it's a gas and it will be living as bubbles, it helps to identify that a reaction has happened. Again, I don't think our reaction is balanced, so we can balance it. We place a 2 here. I think that's balanced. So you can see it again. Acid, this is a carbonate, Carbonate reacts with acid. You get a salt. And now you can see the topic says acid, base, and salt. Automatically, you are getting an idea of what a salt is. How are we getting a salt? It is by a metal pushing out hydrogen, or displacing, or you can say replacing hydrogen. And that's a salt. The compound formed when a metal, or ammonium in some cases, replace hydrogen in an acid. So you get salt, you get water, and you get carbon dioxide. So there are 3 products actually. All right, so we can have one more example. Let's pick another carbonate. This time, let's pick sodium carbonate. For the resulting reaction, you will balance it. Plus, I like using some of these acids which are popular with us, but we can use HCl. So again, remember, a carbonate reacts with an acid. What happens? You get salt, you get water, and you get carbon dioxide. What or how do you get a salt? The metal displaces hydrogen. So come here, take out hydrogen. The metal, what is the metal? Sodium. Pushes out hydrogen, so you get NaCl. That is your salt. You get water, and you get carbon dioxide. Again, you can see we had Na2CO3, that was the correct formula, and now we're having NaCl, that is the correct formula. How did we get it? Watch the videos to remind yourself how to get formula of compounds. So now we can balance this equation. We place a 2 here and place a 2 here. And that balances your chemical equation. And that's it. Acid acid carbonate, triazocarbonates to give us carbon dioxide. But again, remember why it is mentioned as carbon dioxide. There are actually 3 products. So in some cases, some persons, again, depending on who is speaking with you, mentions the 3 products. An example, somebody can say an acid reacts with metals to give salt and hydrogen gas. Somebody says an acid reacts with triazocarbonate to give salt, water, and carbon dioxide. The same thing. But when people mention liberate CO2, it is just because of that proof of a chemical equation. So the next one is what is called neutralization. And what's neutralization? It is that an acid reacts with a base to form salt and water only. It is key to always place in the word only, because I once came across a question, and the question was, why is a carbonate not a base? Well, as you are moving further, you'll be observing these things. A carbonate is not a base, but as I'm going to see later, a base turns red litmus blue. And most carbonates, they also turn red litmus blue. But automatically, that doesn't mean that they are bases. In fact, even some sulfate, like copper sulfate, has the ability to turn red litmus blue. But focusing on carbonates, most carbonates will turn red litmus blue. Not all, anyways. So, the point becomes, that's the property of a base. But does that make it become a base? The answer is no. We'll be discussing bases later, but this is one difference that you can keep in your mind. Why? Look at it. When a carbonate reacts with an acid, you get 3 products: salt, water, and carbon dioxide. But when a base reacts with an acid, you get 2 products: salt and water only. That is one of the principal differences between a base and a carbonate. And remember, we have not discussed bases yet, but for now, how do you get a base? Bases contain metals. It is either hydroxides of a metal or oxides of a metal. They can act as base. They can act as bases. Again, maybe in the next video, when discussing how to prepare acids, you are going to see that we have different types of oxides. We have acidic oxides, we have basic oxides, we have amphoteric oxides, and we have neutral oxides. So some metal oxides, they have the ability to be basic. They have the ability to be amphoteric. But even when they are amphoteric, they still react with acid to give salt and water. So to be on the safe side, all you simply just do is to get a base, pick a metal, pick oxide. Remember to get a proper formula. Metallic oxides are going to be basic in nature, although some are amphoteric, which goes both ways. But either way, since we're talking about acid properties now, they will do and they will work properly for us. So what's an hydroxide? That is the OH. So take the metal, combine with OH. Remember to get their proper formula. An example, if you are saying sodium hydroxide, it will be NaOH properly. But if you are saying calcium hydroxide, it will be Ca and the OH will be inside the parenthesis with 2 as a subscript. So you have to guess those. But to get any base, metallic hydroxide or metallic oxide, and that will work. And then for an acid, remember, an acid dissolves in water to give hydrogen ions. So automatically, every acid must contain hydrogen. So all you simply have to do is Take hydrogen and combine it with a non-metal. That is most likely going to be an acid. As you can see, hydrogen and chlorine, hydrogen and fluorine, hydrogen and you're having some non-metallic radicals, NO3, SO4. Those are acids. So that is the concept. Take hydrogen, combine with a non-metal, that will give you an acid. Take a metal, the oxide or the hydroxide, that will give you a base, and you are good to go. For a carbonate, take a metal, combine with a carbonate, and you are good to go. So for an acid, let us see. Let us say we want to use sodium hydroxide, which is quite popular, combining with hydrochloric acid. It gives us salt and water only, and that process is called neutralization. Remember, how do we get salt? The metal displaces hydrogen. So sodium pushes out hydrogen and you get NaCl plus water, which is H2O. The reaction is already balanced, so we don't stress over that. So that's simply how you get it. So I'm leaving just one example in this case, but you can give yourself so many examples. You can move on and on and on. However, neutralization can be defined in different ways. The most popular one is an acid. We are done with properties of the acids now. These are the three main ones. But I want to give another definition of neutralization, which again I've seen in exams. So we have to note it. Another definition of neutralization. From the word neutralize, what does that tell you? One is trying to cancel out the other. And what cancels out? It is the acidity being cancelled out by the basicity or alkalinity. We'll be discussing bases very soon. So the acidity is being neutralized by the base, or the base is being neutralized by the acid. So what does that tell you? It is the acidic part. And what makes something an acid? The hydrogen. It is being neutralized by the basic part. And what makes something a base? Production of hydroxide ions. So therefore, somebody can simply say that neutralization is the reaction between hydrogen ion and hydroxide ion to give water. Neutralized. You can see this was an ion, this was an ion, now they are neutral. Neutral, neutralized. So that is neutralization. And you can see that's exactly what's going on here. When this guy dissolves in water, you get sodium and you get hydroxide. When this guy dissolves in water, we are already familiar with this one. When an acid dissolves in water, it dissociates into hydrogen ions and chlorine ions. But remember, as I've spoken before, the hydrogen ions do not remain on their own. That will lead us to another definition, which we are going to use. So what happens now? Hydroxide goes to hydrogen and sodium goes to chlorine. You can see the hydroxide and the hydrogen reacting, that is the neutralization. When hydrogen ion reacts hydroxide ion to give water. And in every acid-base reaction, this is exactly what happens. Then, remember I spoke about it. The hydrogen ion, because of hydrogen bonding in water, the hydrogen ion does not stay on its own. Instead, it is combined with water. And when it combines with water, we get what? Hydroxonium ion. So you can say neutralization is the reaction between hydroxonium ion and hydroxide ion to give water. I'm just balancing it in advance, but it's H2O, that's water, then balancing it, balance the number of moles, and you get H2O. So you can see the concept. You can define it, neutralization, as an acid reacting to a base to give salt and water only, or it is hydrogen ion reacting with hydroxide ion to give water, or it is hydroxonium ion reacting with hydroxide ion to give water. Three definitions of neutralization. It all depends on what you want to use. And again, remember, you can see hydrogen ion or hydrogen ion from the acid, hydroxide ion from the base. When they react together, they are neutralized and you get water. All right, and finally, for this video, just want to show you there's only one exception, sorry, where bases react with acid and you don't get salt and water. You get a salt, but you don't get water. And that's the reaction between ammonia, which is a base, and an acid. In this case, let us use HNO3. Ammonia is a base. Reacting with an acid, you have to get salt and water. But in this case, there will be no salt and water. Instead, what you just get is they are combined together and you get ammonium nitrate. This is still neutralization, but it's the one exception where you don't get water. So ammonia is that one base that reacts and you don't get water as part of its product. That reacts with acid and you don't get water as part of its products. So these are the chemical properties of an acid. Next, we'll be discussing how to prepare acids. And then in there, when discussing acid anhydrides, we'll be discussing the type of oxides, like I just mentioned, acidic, amphoteric, neutral, and basic. But before then, you can make some researches. So I'll discuss how to prepare acids, then we can move on to discussing bases, discussing salt, and then we discuss pH.